Okay, good morning, everyone. We will start sharing the screen soon. Okay, so we were looking at example 1. Let me just recall what this thing about. So passengers arrive at a station according to a process NT, person process, and capital T is the departure time of the train, which is fixed. And one needs to find the expected sum of waiting times of customers arriving during 0 to T, capital T. So for that, we want to use the theorem connecting Poisson processes with order statistics concerning uniform distributions. So in terms of that, what the quantity which we need to find is expectation of summation I going from 1 to n capital T of T minus Wi, where the Wi's are the arrival times. So if a passenger arrives at time Wi, the time he has to wait till departure is T minus Wi. So one computes the expectation of such things. So this kind of things are useful in planning how big should be the waiting room and things like that, and about facilities in the waiting room. So we want to use that thing concerning order statistics. So let U1, U2, Un denote IID random variables, each having uniform distribution over 0 to T. So this sequence is chosen for every n, which means we have a master sequence Y1, U1, U2, that's it. And we can assume that this sequence of uniform IID uniform random variables can be taken to be chosen to be independent of the process NT. That is, any UI here is independent of any NT as a random variable. And this can be justified using measure theory. Basically, that means that you take another space on which the UIs can be defined, and then take now the basics probability space as the original space, Cartesian product, that new space, and the probability measure is the product measure. So that kind of strategy helps you to get these things as independent processes. And for these things, one needs the Kolmogorov consistency theorem from measure theory. Okay, so such things are possible mathematically. It is not illegal. Okay, so this is where we had stopped last time. So now the setup is that we have the process NT and we have the IID uniform random variables UI, which that sequence of random variables and this process NT, T varying over 0 to infinity, they are independent processes, independent as, yeah. So now we have to consider this. This is what we want to find. Note that this is this object whose expectation we want to find is a random sum of random variables. Okay. So what we want to find, we would condition this with respect to n capital T equal to little n. The idea is clear because we have a handle on this because of that theorem connecting Poisson processes and order statistics. That is where those guys UIs will come into picture. So condition with respect to NT equal to little n, and then probability NT equal to n. And of course, n can vary from 1 to infinity. So this is fairly clear. So this expectation involves up to this thing, conditional expectation, and here you have the probability and sum over this. Now, of course, this is elementary, simple algebra, basically using the fact that the conditional expectation is linear and this capital T is a constant. And when given that n at t is capital N, here this thing can be replaced by small n. All right, please note it down. So by that theorem, the conditional distribution of W1, W2, Wn given nt equal to n. So we want to evaluate this guy now. This is same as the joint distribution of the order statistics u sub bracket 1, u sub bracket 2, etc., u sub bracket n, corresponding to u1, u2, un. And also these ui's are independent of nt. So this conditional expectation of summation I going from 1 to n wi, n at capital T equal to n, little n, is precisely this by the theorem. This is where we are using the theorem. In this step. So this uses that theorem connecting Poisson process and order statistics. Now here, look here, this summation, it involves all the elements of the order statistics. Given that little n is fixed in this discussion, u sub bracket 1, u sub bracket 2, u sub bracket n, this is, this consists of n random variables. This n random variables is basically some permutation of these n random variables. Therefore, summation I going from 1 to n, u sub bracket I is same thing as summation I going from 1 to n, ui. You cannot do this if this is some k which is different from n. Then that might involve only summation only up to the kth order statistic. Whereas you have basically n random variables. Then it may not be valid. So this is the reason for this step to this step. Consequently, it follows, so please note it down. So it follows that this is now one fairly simple. The expectation of I going from 1 to nt, t minus wi is, as we had seen before, is summation little n going from 1 to infinity. So using this expression now for this, etc. And what we have got in the previous slide, this is equal to this one now. So using that, we have, it is summation little n going from 1 to infinity, nt minus n times half t, the whole thing multiplied by probability of nt equal to n. So this is very simple. And what we have here, so half t comes out. What we have here is basically the expectation of nt. When n equal to 0, there is no contribution here. So summation n going to 1 to infinity of this guy, this thing is same thing as summation as n goes from 0 to infinity. And we know n at capital T has a Poisson distribution with parameter lambda t. And therefore, you know the expectation of nt, that is lambda times t. So this gives you this one. Please note it down. Okay. We will look at this, the way of arriving at this expression, also slightly differently. So that might be useful in certain contexts. Yeah. So in this computation, here we had expanded this out. So without expanding this thing, if you consider t minus wi itself and try to do this. So that is what we are going to see in that remark. So this might be useful to have such a thing in mind. The observation is that ui has a uniform distribution over 0 to t, capital T. T minus ui, you can verify that t minus ui also has uniform distribution over 0 to t. This is an exercise for you. For example, when ui takes the value 0, t minus ui will take the value capital T. So, and the density function, you know, is 1 over capital T. So this you can easily verify. So for any fixed integer n, as we had done earlier, summation I going from 1 to n, little n, t minus u sub bracket I is same thing as this. So now this guy has also uniform distribution. So therefore, ui as well as t minus ui will have all the moments, their distribution is same means expectation will be same, etc., etc. So we have this summation, I mean, the expectation, oh, sorry, if you want to note it down, please do. So now, if you consider this expectation, conditional expectation of I summation I going from 1 to capital NT of T minus Wi given NT equal to N. So you can, that NT you can replace by little n. And by the theorem, we have this, and the UIs can be chosen independent of NT. So using that also, you have this. And this summation, it involves all the UIs. So that is same thing as this. And now you use the fact here that the random variable T minus UI has the same distribution as UI. Therefore, expectation of this random variable will be same thing as expectation of this random variable. So that we already know. So this kind of observation can make sometimes the computation simpler and more transparent. Note it down if you want to. Okay. So we will consider another example. So let us assume that fixed mass of a certain radioactive material is observed. So since it is radioactive, alpha particles are emitted. And this emission of alpha particles is according to time homogeneous Poisson process NT. As we had mentioned earlier, the original experiment of Rutherford, which led to the basic model, the first model for atoms and things like that, was in that the data corresponds to Poisson process that has been statistically found. So NT is the number of particles emitted during 0 to T for every T. This is a random variable. Let us say there is a counter which detects these particles. Of course, the counter's monitor or whatever it is will be at a distance from the source. So for an alpha particle which is emitted to reach that particular screen, if it reaches the screen, it will be recorded. But some of these particles might not be able to reach the screen because by that time they might have perished. Perished means they lose their radioactivity and things like that, are turned into something which is not radioactive. So let's assume that the lifetime of distinct alpha particles form a sequence of IID random variables with a common distribution function, capital G. Note that here, this is the distribution function. Of course, in general, we may assume that the G to be continuous random variable, but it need not be so. So probability, since it is the distribution function, probability that the lifetime of an alpha particle less than or equal to y is capital G at y for every y positive. So this lifetime distribution here of any distinct alpha particle is assumed to be a random variable. Please note it down. So assume that this IID sequence of random variables is independent of the Poisson process NT. Actually, this will be also assumed to be independent of, okay, later on that when a uniform distribution will come into picture at that time. Yeah. Okay, note it. Yeah. So let us fix a little t. So let n sub 1 t denote the number of alpha particles surviving at time t. And n sub 2 t is number of particles which have perished during 0 to t. Of course, clearly, original nt is the sum of these two. For this is, of course, t is fixed. So for this t, we are considering nt and n2t random variables. Okay. Now we are interested in finding this for non-negative integers m and n. We want to find probability n1t equal to m and n2t equal to n. So to compute this probability, we condition with respect to nt equal to j first and multiplied with probability nt equal to j, and then sum over j going from 1 to 0 to infinity. So this summation, you can easily see for only when j is equal to m plus n, it will be non-zero. If j is anything other than m and n, you cannot have that n1t equal to m, n2t equal to n, intersection nt equal to j. since Nt is equal to N1T plus N2T. So in this, so to find this, it's basically this. And this quantity we already know because Nt has a Poisson distribution with parameter lambda t. So our job is to find this object. Probability N1T equal to M, N2T equal to N, given Nt equal to M plus N. Please note it down. Yeah, that's what we have to find. So we want to use that theorem connecting Poisson processes and uniform distribution, uniform and order statistics. So since here it involves Nt equal to M plus N, let U1, U2, U sub M plus N be IID random variables, each having uniform distribution over 0 to T. This again by using that measure theoretic strategies, this thing of having product space and whatever it is, all these guys UIs can be assumed to be those random variables which give the lifetime of every particle. So this, as we had seen even in the example, this thing can be chosen to be independent of Nt. Now here, as well as the IID sequence corresponding to lifetimes of distinct alpha particles. Measure theory sort of gives us license to assume all these kind of things, which make the computation simpler. See, basically in the absence of any kind of any information, one tries to assume certain hypothesis which will make the thing mathematically amenable. Independence of random variables or families of random variables is one powerful assumption which makes many things amenable. And if your observations and experimental data sort of don't contradict that whatever you predict in with these kind of assumptions, then okay, that kind of an assumption is not bad. It's a fairly good approximation to reality. If there is a drastic difference between the predictions using this kind of assumptions and what exactly is observed, then one has to question the independence assumption. So when you have dependent structures and things like that, things can get complicated. Certain kind of dependencies can be handled, or otherwise you have to find out the new kind of mathematical tools to handle such things. For example, mathematically, you might have observed that the concept of martingale is one such, where the summands, if xn is a martingale, xi minus xi minus 1, those guys as I varies are not independent, but they are uncorrelated. And that helps in certain situations. Of course, uncorrelated if the second moments exist. So now with all these kind of assumptions, since we are not interested in all those things, we will assume the kind of assumptions which make this theory to illustrate this theory. Okay. So now by our theorem, probability nt equal to little m and nt equal to little n given capital NT equal to m plus n means probability of, say, these are the guys whose, these are the times are corresponding to emission of the particles or arrival of that thing. Yeah. Emission time and so on. They survive exactly m among these particles emitted at these times survive up to time t. All of them would not have been emitted at the same time. These are the different arrival times. That means different times these particles are emitted. And the rest perish before t. It's possible that the guy who came last may not survive so as to reach the screen, whereas the one which was emitted first might be able to. That's because we have assuming that once it is emitted, they behave independent of each other. So by slight misuse of language, as long as we understand, this is same thing as probability of exactly m among the u1, u2, um plus n survive. That is, this uniform sum of exactly m among these uniform distribution random variables, they live up to the required time. And viewing some survival of at time t as success and perishing before t as failure, some kind of a success failure experiment, this probability is same thing as m plus n choose m. So that is CMN is m plus n choose n, or m plus n choose m. That for convenience, we are denoting it by C sub mn. So that multiplied with probability that the first m guys survive and the last n guys perish. So since these UIs are independent, this will be same thing as product of I going from 1 to m, P UI survives. And similarly here, J going from 1 to n, P of U m plus J perishes. Please note it. So now we will find this product of these probabilities, and similarly this will come. Okay. So UIs are independent of the lifetime sequences. So probability that UI survives for a given I. So this is the lifetime is greater than T minus S, given that UI is S. That is assuming that something like the particle was emitted at time S multiplied with the density of UI, that is 1 over T. Ts. And since the UIs are independent of the lifetime sequences, this conditional probability is same thing as the unconditional probability. And the probability that the lifetime is greater than or equal to T minus S is precisely 1 minus capital G at T minus S. That's why here sort of subtly we are assuming that these are continuous random numbers. Strictly speaking, it's strictly greater than that, doesn't matter. And again, so in this step, we are making a transformation of variable, put R equal to T minus S, and the interval over which the integration takes place is 0 to T. So you can easily observe that this integral is same thing as this. So denote this by P sub T. So P sub T is 1 over T times integral 0 to T 1 minus capital GR dr. Please note it down. Okay. So in a similar way, you can verify that probability that any U of J perishes is 1 minus this PT. So therefore, from in view of what we have already observed here, so this is, so this product is going to be basically m-fold. This probability in probability P UI survives raised to the power m, and similarly here raised to the power n. So probability that n1t equal to m, n2t equal to n, given nt equal to m plus n is m plus n choose m multiplied with pt to the power m multiplied with 1 minus pt to the power m. So basically, in this thing, we are considering from concluding from here onwards, we are modeling these things as a kind of success failure experiment. Survival at time t is called, let's say, success, and perishing before t is failure. So this is probability of exactly m successes in m plus n trials. Where the probability of success is P sub t. So note that this P sub t in this case depends on little t. That's very clear from this expression, right? T is playing a major role. Okay. Consequently, probability n1t equal to m, n2t equal to n is this constant Cmn times pt to the power m 1 minus pt to the power n into this probability. And this probability we know is 1 over m plus n factorial multiplied with e to the power minus lambda t into lambda t to the power m plus n, lambda t whole to the power m plus n. This m plus n factorial and this m plus 1 factorial, they cancel. And pt to the power m and lambda times t whole to the power m, you group together. And also 1 minus pt to the power n and lambda t whole to the power n, you group together. And here also you write lambda times t as lambda times pt plus 1 minus pt times t. So with this grouping and very elementary way of rearranging and so on, you see this is equal to same thing as 1 over m factorial times lambda pt times t the whole power m into e to the power minus lambda pt times t multiplied with 1 over n factorial lambda times 1 minus pt times t the whole to the power n and e to the power minus lambda 1 minus pt times t for every non-negative integer m and every non-negative integer n. Computation is, this thing is very simple, but just check that I have not made any stupid typographical error. So from this, it is clear that n1t and n2t are independent random variables having Poisson distributions with these parameters. So we will stop here for the day. If you want me to go back to any of the slides, I can do that. Because some of these things you might know, I don't know whether you were able to copy it properly. Or any questions, comments? Any comments?
No, sir. So far, so good.
So far, so good. Any questions?
No, not yet.
Any curiosity? Because I thought there would be a question. Okay. What happens if we let this guy T vary? Okay. Okay, we will see those things later. We will see the answers. Because, see, from this, it is very tempting to ask, do these guys themselves form Poisson processes? Okay. But that kind of, for that answer, one needs a definition, because here the PT, etc., these guys are not independent of T. Okay, we will see it. Let's soon. Okay. Sometimes just get bold and ask some questions. Try to guess. Try to guess what might come. The next thing. All right. So now let us stop for the day and see you on Friday.